time is 40 minutes. Maybe by 30 minutes I can finish, and then we can have discussion, or somebody can give me a ring or something. But of course I have my mobile here. I'll also see. Okay, so the coming to the topic, navigating emerging contaminants, key monitoring, health effects, and future challenges. In this area. Well, the organization of the talk is about, I will talk about emerging contaminants. That is for the sake of newcomers or students. Then about monitoring of emerging contaminants. And then finally, I will talk about our own experience on the molecular events in protein pollutant interaction that has direct relevance to toxicology. So what are these emerging contaminants or contaminants of emerging concern? And that is a more accepted word, contaminants of emerging concern. So in brief, we can say compounds which are not yet subjected to regulatory criteria or norms for the protection of human health or the environment is known as contaminants of emerging concern. In simple terms, if the health impact is not known, then you can call it as contaminants of emerging concern. That way also you can call it. So these are a new class of compounds, supposed to be new class of compounds. So whenever a new compounds discovered or in practice, then naturally we have to look at the health impact. So as long as the health impact is not known, not clear, then it will be classified as contaminants of emerging concern. Well, emerging in the history, if you look at the history, the oldest global contaminant was actually lead. And lead production began about 5,000 years ago. And once upon a time, that was an emerging contaminant. And extensive exploitation of lead by ancient Greeks and Romans. And there was a time that if you have more lead in your hand, you are very wealthy. So that was something like a gold now. So that was a situation. So there was an exploitation of lead everywhere. And it's recorded. But what happens is later, that is recorded in the polar ice banks of the era, classical era of Roman Empire. And this figure will tell you that this is from the Greensland ice. You can see from 1800 to 2000, you can see a growing pattern of lead contamination in that region, which actually shows in ancient times people were using it and it has come to the environment. And of course, that time it was actually an emerging contaminant. But now we know the impact of this lead and concerns on contamination of our environment. Lead was detrimental to our health, became prevalent around 70s, 1970s. See, if you look at any kind of such health impact, you can see that around 60s and 70s, because the technology became available and we got sophisticated technology so that you can come to know the health impact. So that's the reason why most of these impacts were known after 1970. So then, of course, the safe was, exposure in children now targeting blood below 5 microgram per liter. And of course, now we have refinement and so on. Similarly, another legacy contaminant, arsenic, again, it was CEC. And arsenic, romantic poison in novels and throughout history, and it was also extensively used. Arsenic sulfate as pesticide in China right from 1980, and so on. Different forms arsenic was being used. But people realized that this is again when it comes to environment, and it is set as 3 microgram per liter, etc., etc. So again, now this is more an emerging contaminant because we know the health impact and so on. Then uh, 60s and 70s and 80s, you have emergence of various pesticides. Initially, it was organochlorines. Then, of course, now it is organophosphate, different other formulations now. So organochlorine, you know the story about DDT, and it was any other molecule, and around 34 or so, Paul Fuller discovered that this DDT can be used against malaria, and right from 1934, he got Nobel Prize for this discovery. This was extensively applied, DDT, and without knowing the health impact. And around 1962, this book published. I hope many of you know this book, Silent Spring. If you don't know it, this actually created the beginning of environmental science. The Rachel Gardner's book. And, initially, they believed that DDT is actually entering into the food chain, and in birds, particularly, she demonstrated this bald eagle of United States. uh, that bird was extinct. That means when the bird hatches the egg, DDT entered into the shell of the egg, started breaking. So naturally, it would go to extinct. So this was actually by Carson. And then, of course, there were a lot of liability against her for this report. Many biosticks all over the world, the DDT industry, very strong, pesticide industry, including the DDT. Believed, but finally, scientific world, proved that this indeed entered into the food and finally into different, higher birds and so Silent Spring facilitated pesticide in 1970, and it was followed by different countries. Then comes, that is actually the beginning, the organochlorines were, and then the process actually organophosphate. Now, around 90s, another discovery, there's a lot of interest in pharmaceuticals and drugs and personal care products. Estrogen, there was a report in 1990, estrogen in sewage as a cause of feminization of fish. And in 2004, there's a landmark report in Nature that diclofenac residue, the cause of vulture population in Pakistan. It's almost like a report by Rachel Carson. And then onwards, particularly from 2004 on, a lot of activity for these drugs, personal care product, the livestock, because a lot of diclofenac antibiotics in livestock, then naturally the vulture is actually eating the remains of livestock, and naturally the bird was getting a lot of antibiotics. Then finally it became an issue, and there onwards, a lot of investigations on COC. So that main classes: pharmaceuticals and personal care product, surfactants, perfluorinated compounds, flame retardant, UV filters, industrial additives, and agent dissolvent and their transformation products, nanomaterials, microplastics, and so on and so forth. So most of the new class of chemicals, when it turns into the environment, then naturally it is an emerging contaminants, and naturally we have to look at the health impact. Well, the possible sources, it's everywhere now. Sources: pharma industry, hospital waste, then household, livestock, and all that, and finally entered into soil, water, air, and everywhere. Then transformation is another issue. It is not only these kind of chemicals, but metabolites. Once it comes to the environment, once it comes to even human body or any animal's body, it metabolizes. And in the soil, air, it metabolizes. Once it metabolizes, it transformed into new class of compounds, and those compounds may be even more dangerous than the starting compounds or less dangerous. It depends. So there's a whole lot of metabolites in the environment where you have to look at these metabolites and the toxicity and so on. Now, globally, I told you it's everywhere. Asia and Indian context, if you look at it, actually there are in UK and United States, there are a lot of reports in the water bodies, and in the sea. In the sea is actually a sink of soup of such antibiotics and all. That is very, very dangerous. And you know why this is that? Okay, I'll come to that. So most of the studies are non-steroidal anti-inflammatory drugs, beta blockers, and antidepressants, and so on and so forth. And this in India, in Asian countries, well, I have prepared this slide almost about 5 years back. Okay, this particular slide. So it is not very true that no comprehensive studies. Now there are a lot of studies from Asian countries as well on the distribution of this kind of drugs in the water bodies. And we ourselves, this our own review appeared in Chemosphere in 2018. Then within a year or so, we got about 150 citations. That so a lot of people started looking at it. And in the Indian subcontinent, we have reported what are these chemicals in different places. And when I reported this in 2018, of course, not many reports were there. Now there are a whole lot of reports, different groups are working on it. And now we are better off with the literature. Now, why are we concerned? You can imagine that if you are getting a drug or antibiotics, talk about antibiotics, if it comes to the water body, then naturally this antibiotics will come to fish. And from the fish, it will come to human. We eat fish, then naturally every day basis you will be getting antibiotics in your body. So a free service that you will be getting a lot of drugs in your body, then what happened is you develop antibiotic resistance. So no other antibiotics may not work. So, well, this is an exaggerated statement, but at the same time, it is highly probable that even very low concentration of antibiotics, if you are getting antibiotics in your body, then it is a dangerous situation. That is the reason why, right from 2010 onwards, the World Health Organization declared that this is a menace, and then they have actually warned globally that this is going to be an issue right from 2010. So this is the one. So based on this, we have a couple of programs in our laboratory. We have screening programs in water bodies in South India, and we also monitor this kind of compounds in drinking water in Kochi area. Kochi is one of the biggest cities in Kerala. Where we have a lot of, the Kerala is blessed with almost about 44 rivers, and then of course the seashore, then all kinds of canals, large number of canals and all. So that we are actually monitoring this kind of compounds there. Then also we are looking at the transformation of this kind of pharmaceuticals in natural conditions. How these pharmaceuticals are getting transformed due to sunlight, due to microbial transformation, and all that. Then we are mainly concentrating on Periyar River, Vembanad Lake, one of the biggest lakes, and also we are looking at the Arabian Sea with the help of some, Navy and all. We are getting samples from Arabian Sea and looking at presence of these compounds. And another interesting area is Arctic region. We are part of the Indian Arctic expedition. So every year our students and faculty, we go there. We stay there for about 40 days or so in the Arctic region, where India has a research station called Himadri. There are about 10 research stations in Arctic region along different countries. There also we get samples from Antarctic region, and we are monitoring such compounds. Another important area we are looking at is advanced oxidation process for the degradation of this kind of compounds. Is a water treatment program, which is very different. I'm not going to talk about it today. Then another program is protein pollutant interaction. So we are trying to see the molecular basis of toxicology, where what happens to the conformation of the protein when such compounds, emerging compounds, interact with proteins. So these two programs, I'll talk about two programs if time permits. So this kind of compounds, pharmaceuticals and personal care products, can be analyzed only by mass spectrometry, highly sophisticated machines. These are generally analyzed by ultra performance liquid chromatography. That MS is connected to liquid chromatography, so the initial separation will be done by chromatographic. Then it goes to the mass spectrometry machine, MS machine, and then you require high accuracy mass spectrometry. Then sensitivity and specificity of environmental analysis can be improved by application of tandem mass. Tandem mass means, generally, if you know about this machine, it directly gives the mass value. You can fragment a molecule first, then you look at different fragments, and you can take each fragment, then fragment again. That is actually second fragmentation. That is called tandem mass, MS. And hybrid, there are a lot of sophisticated machines now. Then confirmation of the identity of the target compound by monitoring two characteristic precursor product transition. Then also triple quarter pole. Now the latest machines are quarter pole machines, triple quarter pole machines, like time of flight machines, then LCMS, liquid chromatography mass spectrometry, then LCMSMS, that is the tandem mass, time of flight machine, and so on. All this you can use for detecting these compounds. This is our mass spectrometry lab. We utilize these machines for this kind of measurements. We have a normal LCMS, we have then LCMSMS. MSMS, the advantage is that you can go deep into even picomolar range and find out the sensitivity is so high. Then we have LCQ of time of flight mass spectrometry, where you can have this structural elucidation. For unknown compound, you need high resolution mass spectrometry. And also we have GC for polar compounds, and we have also GC MSMS, and also we have ICP-MS. ICP-MS is for elements. You can scan almost all elements with ICP-MS. So this is the machines we utilize for this kind of work. Then for mass analysis, there are two kinds of analytical protocol. One is targeted analysis. Targeted analysis is very easy. That means if you have the standard with you, if you have an unknown, you inject into the machine, then you can also inject the standard, so that you can easily come to know that whether this particular compound is in the mixture, unknown mixture. But non-target analysis is a very different protocol, and that is actually being used for detecting these kind of compounds, because often you do not have the standard with you. It is extremely difficult to get sample. You can have whole lot of hundreds of metabolites. Definitely you won't have any kind of standard. So you always go for non-target analysis. And non-target analysis is mainly utilized by high resolution MS. High resolution means, well, for students, I can tell you that the accuracy goes like this. Say mass of a phone is 300. Okay, so 300 you can have thousands of compound with the same, but 300.2 you can reduce to 150. Okay, then in annual digit 300.25, you can cut down to maybe compound. Then 200.253 digits. Then naturally 50 compound. Then 300.2532 digit. Then naturally it comes to less than 10 compounds, where you can get an idea. Then if you can go for, we have actually this 4-digit mass machine, generally 4-digit mass machine, you can go up to 6-digit also. Okay, it's extremely, accurate and so on. That is first step. That is not all. Then we use energy resolved spectrometry. Of course, I'm not going to the detail, where normally certain fragments at a particular energy, you can change the energy in the machine, then you can get a different mix of pattern. So again, so it is called restored spectrometry, where you can get better idea on these compounds. Then also, in certain cases, you have to go for theoretical calculation. Because unknown compound, if you want to report, because adds error. This is the issue with non-analysis. This is the issue with MS. Okay, so the analytic procedure is very. Certain cases we go for density theory calculation to really see the energy of this fragment. So these are some of our recent publications. If somebody wants, we can share it. Now, what non-target analysis is in water bodies? One is many unknown. Many unknowns. Then complex matrix. You go from one to other different matrix, maybe salt and all kinds. Then too little compound there. So this is why we go for non-target analysis. A lot of challenges I already told you. Still, no specific protocol for NTA. No MS library. It is the MS library like GCMS that you just look at the library and connect with that. Then similarity in MS. For example, you have isomers. When you have isomers, you get the same marks. Absolutely no change. How do you distinguish it? That's another problem. Then, so you have to see the positive ionization, negative ionization. So you have to see both the modes. Then interpretation of data, you require extreme expertise. The list of suspects are expected. You have to guess some kind of interpretation also. In certain cases, you have solved dependent fragmentation. We should be very careful. Then in certain cases, if you change the solved fragmentation, it may not differ, might differ. These are all extreme complicated when you look at this with compounds. Then there is another issue that you find out, maybe you take 6 months to 1 year or 2 years to get some good compounds. This report, I know that almost for 15 years, 20 years, when you report 2 CECs using MS, you used to get accepted in applications. Now you have to report 200 also. The editor asked, what? So extremely difficult to teach students to work in this area because with all kind of analytic challenges, come out with some compounds, and people ask. This is another part of the story anyway. So, but still, yeah, so we should be successful. Analysts are successful in doing this. ppm error limit, you can, in this case, maybe about within 5 ppm error, then you will have better confidence. Careful observation of this MS data, positive and negative. So then one thing you have to be careful to look at instrumental parameters. It's very important. If you don't look at instrumental parameters, it is extremely difficult to read control. So in a limit of detection, limit of quantification, then standard deviation, right? So this is actually an analytical part which I'm not going to detail. Also, we look at theoretical one. Example I want to show you that is not universal, but in our compound we have determined, we have actually designed a methodology to distinguish the position isomers. Now, this is mainly with the theoretical calculation and energy resolved mass spectrometry, where we can distinguish meta, para, ortho compounds. So that is of course with this kind of technique. Then, of course, also we found the solvent-dependent issue because in certain cases that there you get some wrong idea that when you change the solvent, you get a different pattern of degradation. Then these are the normal extraction procedure, which are generally accepted procedure for any kind of extraction. It's called Kitcher's extraction. It's not a name. Quick, easy, cheap, effective, rugged, and safe. That is Kitcher's extraction procedure. Then you use solid phase extraction. Well-known extraction using a cartridge. That means you concentrate. If you take 2 liter and then you concentrate to few ml, so that you get a better concentration. Then the machine we mostly use is this time of flight machine, a waterfall time of flight machine. Well, this one example I want to show you that this is actually one of the South Indian rivers, Periyar River in Kerala, which is actually supplying water almost about 1 million people in that area. But at the same time, there's an industrial. So this output is called the total ion chromatograph, and then each chromatograph can separate, and then each chromatograph we can undergo, each fragment can undergo multi fragments, and that's what I said MSMS. Okay, so these are the compounds detected. You can see a lot of compounds right from base and up kind of compounds, very low concentration. Identified. We have also quantified some compounds where standard. You can also see that it's very comfortable and good-looking chart. In this water body, then this kind of compound. Then quickly going. Time is limited. I think 10, 15 minutes more. So in the present study, we identified 37 compounds which are included in the category of pharmaceuticals and personal care products, UV filters. Yeah. This is one part. Then again, I'm not going to the details. We have a program from Arctic region. This region, we collect the Arctic. We collect from Arctic to sea, and also we collect the sediment into about half a kilometer, 1 kilometer in the sea. The sediment we collect and like this area, Arctic area, you can see that research stations, 10 research stations associated buildings. This is called Sweden, Alison, this area. Some of you might have heard. It's a small island close to Arctic. So sample from there. So finally, I'll tell you, we have sampling stations. There we got this similar kind of analysis. We have slightly changed the protocol. There is ice. Also, it has salt content. So we have detected bisphenol S, surfactants, and other compounds in that area. Multiple reasons, sea current or human activities, and so a lot of reasons you can point out, but still, because it's already known that pesticide use are there in both the places. It's actually the first report related to pharmaceutical region. Okay, next in another 5-10, I will concentrate on this health aspect. You can see all this, a whole lot of chemicals, different chemicals, and actually when it comes to, it is already there, soil and so on. Now, finally, it's in human body and animals. So So you can see a lot of such issues, from neurotoxicity and all kind of things. It could be due to environmental factors like chemicals, or it could be due to other factors. So, one example which I want to highlight, which is taking place in our laboratory, this is already published last year in Journal of Hazardous Material, uh, understanding the conformational transition in serum leading to amyloid precursors in presence of emerging contaminants. So three-dimensional. In brief, I want to tell you three-dimensional shape structure human protein is very important. In the sense, there are a role for protein due to this structural identity. Okay, then also it moves. Okay, that's also it is necessary to have certain. Okay, so alteration in protein's conformation increases its activity and cause strong tendency to aggregate. Important. So we are actually looking at this kind of aggregation of protein to emerging contaminants. Okay, this is a kind of molecular. This actually causes neurodegenerative disease. Now it is well known that most of the neurodegenerative diseases are due to this protein aggregation in the brain. And almost about 600 are reported, right from Alzheimer's to Parkinson kind of diseases are due to this protein aggregation, due to various reasons. Okay, not only due to various reasons. So protein misfolding can be initiated by a number of environmental the formation of fibrils. Through intermediate like glomer protofibril, mature fiber, this will lead to neurodegenerative diseases. We are actually looking at this kind of intermediate species. We have selected two compounds, two proteins, DSI and HSI, cellular proteins. And these proteins have about 50 to 70% alpha helix. And there is actually a proportion alpha helix and beta helix. And generally, alpha helix is more than beta helix, less. Then we have selected a series of compounds. I am not talking about all compounds. Glyphosate, okay, the emerging contaminants, aminomethyl acid is actually a product of glyphosate. Whenever there is a glyphosate concentration, it is associated with AMP, it's metabolized. Then Roundup, and so on. So we have done a series of studies. I just want to introduce that studies. I'm not into the details of the studies. Binding studies, you can use UV visible spectroscopy, UV-state fluorescence spectroscopy. Then for confirmation studies, you can use synchronous fluorescence. I'm going to stop in 2-3 minutes time, don't worry. Then binding mechanism at the TCSP, that is time correlated single photon counting. Then morphological characterization with AFM, atomic force microscopy. Molecular blocking studies, again with theoretical studies. These are the machines we use, Raman microscope, spectroscope, and then other UV, fluorescence, time resolved, etc. Well, I'm not going to, since due to the lack of time, I'm not going to the result, but I'll come to the final point. This is actually fluorescence hinging result. Then this is about stain former. You can see the change in the step. If you know photochemistry, then this actually change in the linearity, which means that it undergoes additional site of binding with this kind of compounds. Then time, that is fluorescence studies, where you get different components which will give you different environment of the compounds. This is actually the synergistic dynamics of the molecule. Then even UV visible, I already told you. This is one picture maybe you have to see, that PSA and glyphosate, if you look at, is actually time evolution of the AFM. You can see that initially it's a monomer, then goes to oligomers, then protofibril, and finally complete collapse to fibrils. Okay, so this is there's a complete collapse. The second one, if you see PSA AMPA, that is actually the metabolites, monomer, then compact network of oligomers. It is not going to the fibrils, but it is actually oligomers, tetramers, and so on. Then, of course, this also goes to amorphous, this one with the roundup protein is going to the amorphous state. Then, of course, Raman spectroscopy is basically to see the shift. You can actually see the shift, and also you can study the secondary structure of protein. That's it. Okay, you don't have to worry about this picture. I'll come to the last slide, the conclusion, where we have used these kind of compounds, glyphosate, AMPA, Roundup, and so on. You can see the first one, glyphosate, finally it goes to fibrils as a complete collapse. But for AMPA, you can see that compact network of oligomers, it is not going to fibrils, but it is getting in the same shape. Now, the danger is when you have these oligomers, trimers and tetramers, it can break the brain barrier. That is more dangerous. Once it breaks the brain barrier, it will go to neurodegenerative diseases such as Alzheimer's and so on. And it is well proven that this kind of mechanism will lead to Alzheimer's. So what we are trying to say is, this kind of compounds, when it interact with the proteins, definitely it could go to this kind of compounds, and it can break the brain barrier, and then it go to the neurodegenerative diseases. Remember, this is only an in vitro study. Okay, so you can't really conclude that this is a final. Okay, because you need to have in vivo study to prove that this is taking place. What we have actually reported is some of the steps involved, and probably that will be there in the cellular medium that we are actually currently working on in vivo studies. So this is the final point. Then, of course, it is too late, but still I am just showing you that we have a water conference in our place, December 12 to 15, 2024 in Kottayam. Bit late, but still I just wanted to show you this. So thank you very much. Since there is no chairman, I myself ask you if you have any question. Yeah. Yeah, please. Yeah. Yeah.
We shouldn't have any lead exposure at all.
Yeah.
And from the graph that you showed, there's a peak of lead, I think, in the Arctic, in the 70s, 80s, something like that.
Okay. That is, of course,
what did you thought the basis of that was, considering the sort of phase out of?
It's from the lead pollution.
Yes.
Yeah. Okay. That, in fact, I have taken from the literature. I'll come to that. You mean it is not linear?
Well, it's just that why do we see that? Or what do you think the basis is of that sort of?
It's the only reason I can find. This one. Yeah. The only reason what I find is the experimental issue. Because that region, this was actually published by a group from Sweden or somewhere long back. So there, because they were looking at the ice about 1 meter down, So where now, of course, what people do is you actually you take a column. So different column, then naturally you get different average. This one, you will get a better better picture. So this could be one of the reason that where there's a hike. This one, yes, yeah. 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 There are different factors. I told you there are different factors for this kind of aggregation, not only these chemicals. But one of the possibilities where we have to do this model, animal model, then only we can conclude it. Here what we have done is a direct interaction. And direct interaction is very different compared to interaction within these cells. So, but still this is important in the sense, only this is important in one sense, that in certain compounds, there is a complete fibril formation, which means that we know that it's toxic, okay? Then it will not, for example, very low concentration of these compounds. This is the one which I have shown you, right from very low concentration to high concentration, the only oligomers are formed. If there is a situation like in human body with very low concentration of this kind of compounds, if oligomers are formed, it might really go to the brain. So that is the important, that is why this is also accepted. I mean, this, and it is now getting a lot of citation for this paper also, that material. Yeah.
Serum albumin added with the glyphosate.
Yeah.
Is there any information about how it is interacting with the amino acid specific?
Yeah, it is interacting with amino acid only.
Yeah, that's
See, basically, that I didn't have time. That we are actually concentrating on 3 amino acid because the fluorescence come from amino acid, and fluorescent quenching means there is direct interaction with the amino acid. Okay, and also we have done some docking studies where there is a one-to-one complex formation. There's a collapse of that, that hydrogen bonding, and then there is some other interaction which actually goes to a kind of direct bond formation. That's also there. So that's the reason why it's like a strong quenching of the fluorescence. At this moment, we can go for other technology to find out which protein. That of course no.
Enzyme digestion method and
Yes.
mass spectrometry.
Yes.
Another one more last question of me. And you showed that bisphenol analysis in sediment.
Sediment, yeah.
Sediment. What is the extraction protocol? Because sediments has a lot of humic material also.
No, see,
how do
I extraction protocol is this SPE only. I mean, solid phase extraction with some changes. For example, I told you that there are some salt concentration in that. So there are some steps by which we remove the salt also. And then matrix, what we do is actually we do the matrix isolation technique also. So then we look at how far we can extract. So we standardize it, and sometimes blindly we do SPE. Okay, blindly we do. Then what we do is the same procedure, we use it with either standard. And if we can extract with, like maybe comfortably 90%, so within an error limit of 10 to 20%. So there is actually error limit, which we can, confidently say this. And this is actually established also now.
Over.
Oh, thank you. Over.
Thank you, sir. It was a very insightful session. Now, may I call upon Mr. Jan Anderson for the next presentation?